Here's another one of our videos about gases. In this video, we're going to talk about the combined gas law. The combined gas law. So the combined gas law is going to help us relate things we can measure, like the volume and temperature and pressure of a sample of gas, with an equation that tells us the relationship between those things and allows us to do some calculations. There are a number of gas laws that can give us the relationship between two different properties of gases. So for example, we can relate volume and temperature using this equation. It turns out to be a direct relationship. When the temperature of a sample of gas goes up, its volume goes up. That relationship is true. It only works when pressure and the number of particles of the gas are constant. And this is called Charles' law. We can make a relationship between volume and pressure of a gas. There's an equation that relates volume and pressure. That turns out to be an indirect or an inverse relationship. That means when the pressure on a gas goes up, the volume of that gas goes down. That relationship is true when temperature is constant, and it's true when the number of gas particles are constant. Boyle's law is the name given to that relationship. And we can also make a connection between temperature and pressure. There's an equation that turns out to be a direct relationship. When the temperature of a gas goes up, the pressure that it exerts goes up. That relationship is always true when volume is constant and when the number of particles in the sample of gas are staying constant. This law is attributed to Gay-Lussac. So let's think about this scenario now. Suppose we have a balloon and it rises high into the air. And by high, we mean many thousands of feet. So here's a picture of Mount Fuji, which is a very tall mountain, thousands of feet tall. And we would expect that as this balloon rises to the kinds of heights of a mountain like Mount Fuji, that the temperature would go down. That high altitude temperature is generally lower. And we can see that from the picture of mountains. Maybe we've been on a mountain that has snow on it at the peak, when it appears to be spring or summer down below. It's colder at the top of the mountain. And the pressure is also lower as we go up very high into the atmosphere. And we know that because we've heard stories about mountain climbers who have difficulty breathing. People who are in the Himalayas, for example, have a hard time breathing when they're climbing the tops of very tall mountains. So as this balloon rises very high into the air, the temperature goes down and the pressure also goes down. Well, let's think about our gas laws. We've heard that when the temperature of a gas goes down, its volume goes down. Temperature and volume are directly related. We've also heard that when the pressure on a gas goes down, the volume goes up. Pressure and volume are inversely related. So what's going to happen to this balloon? The temperature is going down, the pressure is going down. Is the volume going to go down, or is it going to go up? For that, we need something more than our laws that relate to properties of gas. For that, we need the combined gas law. And the combined gas law is going to make a connection between the temperature, volume, and pressure of a gas sample when all three of those things are changing. So here's a mathematical expression for the combined gas law. It tells us that if we take P1 and multiply it by V1 and then divide by T1, we'll get the same thing as if we take P2, multiply it by V2, and divide by T2. So P1, V1, T1 are properties of the gas measured at the same time, early in our experiment or at the beginning of our problem. And pressure 2, volume 2, temperature 2, these are properties that are measured later on in the experiment or at the end of our problem. Now, for some people, fractions are a little daunting. We can use what we know about algebra to rearrange this equation, and we can write it in this form down here. Pressure 1 times volume 1 times temperature 2 equals pressure 2 times volume 2 times temperature 1. Very important to pay attention to the subscripts. Before we actually use this law for a calculation, let's think about the units of measure. So for pressure, we can use any units of pressure that we want to use. However, pressure 1 and pressure 2 must be expressed in the same units of measure. We can make a similar statement about volume. We can use any units of volume that are convenient for us, but V1 and V2 have to be in the same units of volume. Temperature is different. In order to do calculations and using the combined gas law, we must have our temperature in Kelvin. Oftentimes in science we measure temperature in degrees Celsius. To get it into Kelvin, we have to take the number of degrees Celsius and add 273. All right, let's try a calculation with the combined gas law. So here's a little scenario. Suppose we take a weather balloon and we fill it up. We're going to fill it with helium because we want it to go up in the air. And when we fill it, the pressure is 1 atmosphere and the temperature is 16 degrees Celsius. We're going to fill this balloon until it has a volume of 825 liters. And then we're going to let this weather balloon go. And it's going to rise very high into the sky. The balloon rises high into the atmosphere. And when it does, the pressure that it experiences is going to go down. It's going to go from 1 atmosphere down to 0.75 atmospheres. And at the same time, the temperature is also going to go down. So the temperature high up in the atmosphere is minus 15 degrees Celsius. What we want to find out is what's the new volume of this balloon. So we can take the words of our problem and we can figure out some of our parameters to put into our combined gas law equation. And we can read the problem and we can find out that volume 1, the initial volume of the balloon, 825 liters. Temperature 1, 16 degrees Celsius when the balloon was first filled. We add 273 to that. The initial temperature is 289 Kelvin. The pressure when we filled the balloon at the beginning of the problem was 1 atmosphere. What happened to this balloon? It goes up in the sky, the pressure goes down, the new pressure is 0.75 atmospheres, the new temperature is minus 15 degrees Celsius. Remember, we add 273 to minus 15, that gives us 258 Kelvin for our new temperature, and we want to find out the new volume. We don't know the new volume at this point. An ideal problem, a perfect problem for the combined gas law. So let's see what our combined gas law is. There it is right here. We're going to use the multiplication version of this law and we're going to substitute our data into this equation. Pressure 1 was 1 atmosphere, the original volume 825 liters. The second temperature, 258 Kelvin. The second pressure was 0.75 atmospheres. We don't know volume 2, that's our unknown, and 289 Kelvin was our original temperature. Okay? So now we're going to take this equation, we want to isolate our unknown, our V2, and we can do that by dividing both sides of this equation by 0.75 atmospheres. These are fractions. And we're also going to divide by 289 Kelvin. We do that, we can cancel out some units of measure on this side of the equation. We can cancel out some terms on that side of the equation. And what do we end up with? We end up with something that looks like this. Volume 2 equals 1, the number 1, times 825 liters times the number 258, and then divided by 0.750 divided by 289. So we do that calculation and we find out that volume 2, the new volume of the balloon when it gets high up in the air, is 982 liters. So what happened to our volume? It went up. But we couldn't necessarily have predicted that just by thinking about the direction that temperature and pressure changed in. We had to use the combined gas law to make a calculation of what happened to volume. So again, the combined gas law helps us out when the pressure of a sample of gas and its temperature and its volume are all changing at the same time.